Salve Ivo, come vai? Mi
Welcome.
ascolta? Così, non la camera.
Hi, Carlos. How are you?
Okay, so welcome everybody. Well, good afternoon, good evening, or good evening. My pleasure. Sorry, I'm going to mute most of the participants. Welcome to everyone. I'm Dr. Norville Melachu, current ICOH National Secretary of Peru, and it's my pleasure to welcome all of you to participate of this webinar with such great speakers that comes from the Scientific Committee of Nanomaterial Workers Health from ICOH, and we are very delighted to start this webinar because nanotechnology has contributed a lot in the advances for health, but also for biology and engineering. And nanotechnology's properties, like their extremely small size, present new occupational health risks for workers exposed to nanomaterials through inhalation, thermal contact, or ingestion. Although potentially dangerous and very risky, they remain not so well known for many of the workers from different sectors. And that is why we have organized this webinar in order that we can promote information about this and to start maybe collaboration between countries to get involved in not only working in favor of workers exposed to this nanomaterial, but also to cooperate maybe in future research or projects in favor of workers' health. So for starting this webinar, we would like to express our gratitude for the ICOH Scientific Committee of Nanomaterial Workers' Health and to all our speakers that we will be presenting today. For instance, we are going to introduce to Dr. Cecilia Colauti, who is a physician specialized in labor and legal medicine, dedicated to promoting occupational health and the prevention of occupational hazards. She's member of Women in Global Health from Argentina, contributing to initiatives that promote gender equality and health in workplace. Her experience also includes teaching in the Army Engineering faculty, where she addresses critical topics such as occupational toxicology and professional illness. For more than 2 years as Scientific Secretary of the Scientific Committee on the Health of Nanomaterial Workers, she has collaborated on investigations and strategies to mitigate emergent risk. Her mission is to support teams and organizations in the construction of safest, healthiest, and most equitable workplaces, integrating occupational health risk management experience in safety, hygiene, and nanotechnology. So welcome, Dr. Cecilia Colauti. It's a pleasure to have you here. I will stop sharing so you can share your screen.
Okay. Thank you so much, Norville. Good afternoon, everyone. Let me see if you maybe... You can see my...
Yes, now we can see your screen.
Yes. In a minute, please. I don't know what's happening with this. Please. You can see it.
Yes, now we can.
Yes. Oh, well, thank you so much. It's a great pleasure for me to introduce you to our Scientific Committee on Nanomaterials Worker Health from ICOH. I'm the secretary of this committee, and Dr. Beluska Les is the president, and Dr. Iboyabikul is the past president of this committee. Our committee was created with a a clear mission to promote and advance research, education and policies that improve the occupational health and safety of workers exposed to nanomaterials. And why it's matter? Nanotechnology is rapidly transforming industries from electronic and medicine, energy to construction and etc. You have a lot of industries with nanotechnology, and this adds at the unique properties of nanomaterials that brings a lot of extraordinary benefits, but also have a new complex risks to the health of workers exposed to this kind of materials. First, I want to be clear that our committee brings together occupational physicians, scientists, toxicologists, engineers, and policy experts from every region of the world to working to promote and evidence on basis research education and policy development. And our core activities are related to research and evidence, data and exposure, toxic generated data to toxicologists and exposure and health outcomes, the guidelines and prevention, contributing to international guidance from safety and healing of nanomaterials, education and capacity building with trainings, with webinars like this, we educational results, and the global cooperation or collaboration, connected researchers from all over the world, practitioners and policymakers. Oh, sorry, it's not what idea. And I would like to invite you, and as we look the future, I would like to invite you to join us, attending our webinars, our congresses, seminaries, contribute with your findings, with collaborating with the result, and help us to carry out preventive actions and strategies that balance the innovation with the human health. In the words of the Richard Feynman, one of the pioneers of nanoscience, but I can not create, I do not understand. Maybe let us create understanding of this kind of risks that we can generate knowledge about toxicology for nanomaterials, and this very small world can help us to have a healthier and safety future for all the workers. Thank you so much, Norville, and I let you with very, very distinguished speakers on this afternoon.
Thank you, Dr. Cecilia. Thank you for all your support in the organization, also for this webinar. And we know the importance and the impact that this type of events can have in our daily job as occupational health professionals, not only for physicians, but also for nurses engineers and biologists and the rest of professionals. So thank you, Dr. Cecilia, and I'm going to introduce to our next speaker. Oh, I will share the screen. Okay, so it is my pleasure to introduce you to Dr. Veruska Leso. Dr. Veruska Leso is an assistant professor in occupational medicine at the Department of Public Health of the University of Naples, Federico II, and a medical doctor at the Occupational Medicine Unit of the University Hospital Federico II in Naples, Italy. At the Catholic University of the Sacred Heart of Rome, she obtained her degree in medicine and surgery in 2007 and her specialization in occupational medicine in 2012. At the same university, in 2016, she obtained the title of Doctor of Research in Occupational, Environmental, and Social Medicine. She was secretary of the Toxicology of Metals Scientific Committee on the International Commission on Occupational Health, ICOH, for the period 2018 to 2024. Actually, she is the chair of the Nanomaterial Workers' Health Scientific Committee for this triennium. The main themes that characterize her research activity concern the toxicology of metals, even in nanometric dimensions, the environmental and biological monitoring of occupational exposures to xenobiotics, the evaluation and management of chemical risk, the health promotion in the workplaces, and the impact of chronic pathologies on the working capacity of affected subjects. She is author of over 100 scientific publications in national and international journals. Welcome, Dr. Veruska. It's a pleasure to have you here with us.
Good evening, everybody, and thank you, Dr. Merachu, for the introduction and for the opportunity to be here this afternoon. Can you see my screen?
I think it is still loading, Dr. Veruska.
Can you see?
Not yet.
I'm sorry. Can you see now my screen? I think so.
It is loading. Now we can see your general screen. Now we can see the presentation. Now we can see.
Okay. It works.
Thank you.
Okay. Thank you all. And as most of you know, according to an European recommendation that was promoted in 2011 and updated in 2022, nanomaterial means a natural, incidental, or manufactured material consisting of solid particles that are characterized as their own or as aggregates or agglomerates for the 50% or more of their particle in particles that are characterized by one or more external dimensions in the size range 1 nanometer to 100 nanometers. Engineered nanomaterials are characterized by peculiar physicochemical properties that offer them the opportunity to make products stronger, more conductive, lighter, and generally smarter. And so engineered nanomaterials have found application in many sectors and commercial products, including, for example, the automotive, chemical, construction industries, but also the electronic, energy, and textile sectors, biomedical products, and cosmetics. This increasing application of nanomaterials inevitably increased the likelihood for the exposure, both in general living and occupational environments. Concerning workers that are at the first line of exposure with respect to nanomaterials, Workers can be exposed during research activities in academic and commercial labs, but also during operations in startup or scale-up operations, while manufacturing or producing nanomaterials, as well as during the incorporation of nanomaterials into nano-enabled products, but also the disposal or the end of life and recycling phases of products containing nanomaterials can be occasion of exposure for workers. This increasing likelihood for occupational exposure raised concerns about possible adverse effects of nanomaterials. These concerns have also been motivated by previous evidence concerning the adverse effects of ultrafine particulate matter derived from air pollution and epidemiological studies, data extrapolated from investigation on the health effects of diesel and welding fume exposure, but also were motivated by the preliminary toxicological results concerning engineered nanomaterials derived from in vitro and in vivo studies, demonstrating the action, the inflammatory and oxidative stress reactions induced by nanomaterials and several organ damages that nanomaterials can cause. But to deeply understand the impact of nanomaterials on health, it's an extremely challenging issue because of the heterogeneity of nanomaterials that have a great variety of physicochemical properties, both primary and secondary acquired properties once the nanomaterials enter in contact with biological fluids. We generally don't have enough information on the type and quantity of nanomaterial exposure. We don't have standardized strategies for the environmental and biological monitoring of nanomaterials exposure. And generally, we don't have sufficient or definite knowledge concerning nanomaterial toxicokinetics and dynamics. And there is also an intrinsic difficulty in assembling study cohorts to assess health outcomes, because generally the production of nanomaterials is decentralized, and so a limited number of workers in each facility are engaged in such kind of activities. Concerning the health effects, it's not difficult to understand that the respiratory effects have been the most investigated in literature, because the inhalation route of exposure is the primary route of entry in occupational nanomaterials in occupational settings. In this sense, in this regard, different studies have found significant, although not pathological alterations in the lung function parameters in exposed workers. For example, a reduction in the forced expiratory flow, or for example, in the ratio between the forced expiratory flow and the forced vital capacity, and peak expiratory flow as well. These findings have been reported in nanoscale carbon black and titanium dioxide nanoparticle exposed workers, and particularly after periods, some periods, longer periods of exposure, 6 months, for example, of follow-up. Other studies failed to demonstrate such difference in lung parameters, lung function parameters, and these conflicting results in literature may be derived, may be explained by the different kinds of nanomaterials, so the different types of exposure and the different moods of the exposure during the work activity. Concerning other possible adverse effects and symptoms, for example, the only significantly more prevalent symptom among exposed workers exposed to titanium dioxide, silica dioxide, or gold nanomaterials or carbon nanotubes was sneezing. That showed a higher prevalence, a significantly higher prevalence in exposed workers compared to controls. Allergic dermatitis was also significantly worsened by handling nanomaterials in exposed workers compared to controls. And also cardiovascular effects have been reported, as low frequency of heart rate variability was found associated with occupational exposure to different kinds of nanomaterials. In this uncertainty scenario, human biomonitoring can find a possible application. Biological monitoring, for example, defined as the repeated controlled measurement of chemical or biochemical materials in fluids, tissues, or other accessible samples from subjects exposed to chemical risk factors in the workplace, can be useful through biomarkers of exposure and biomarkers of effect in understanding the continuum between the exposure and the development of early effects and organ damage. Concerning possible biomarkers of effects, occupational epidemiological studies supported the possibility to employ, for example, white blood cells count or pro-inflammatory cytokines, for example, or the urinary concentration or the exhaled concentration of the 8-hydroxydeoxyguanosine, for example, or the serum level of antioxidant enzymes as possible biomarkers of the inflammatory and oxidative stress reactions induced by nanomaterial exposure by different kinds of nanomaterials like carbon black or synthetic amorphous silica or titanium dioxide. Concerning early biological effects, for example, the serum surfactant protein D levels or nitric oxide, or the serum intercellular adhesion molecule 1 or the vascular cell adhesion protein 1 have been identified as possible biomarkers of early damage at the level of the respiratory tract and the cardiovascular system. A couple of considerations, anyway, should be pointed out considering these possible biomarkers of effect. The first one regards the sensitivity and specificity of such type of biomarkers, because most of them can be affected by or can be influenced by external insults. And so other external insults can affect these biomarkers. They are not specific for nanomaterial exposure. At the same time, the definition of suitable biomarkers requires a deeper knowledge concerning the nanomaterial toxicokinetic and toxicodynamic profile. Concerning genotoxic and epigenetic biomarkers, DNA damage was detectable and was demonstrated in workers involved in the production of graphene and silica dioxide nanoparticle through different tests. And also, although not the literature data are not homogeneous, are not in this regard, because several articles found no difference in genotoxic effects induced by nanomaterials, but also epigenetic effects have been reported. A significant reduction, for example, in global DNA methylation was determined in silica dioxide nanoparticle exposed workers, but also there was unaltered methylation patterns at the GPG sites in promoter regions of genes involved in epigenetic regulation, DNA damage response, cell cycle control, oncogenic pathways, for example, in multi-wall carbon nanotube exposed workers. But also, this kind of exposure was able to induce significant alterations in global expression profiles of non-coding RNAs or microRNAs engaged in regulating cell cycle progression, apoptosis, and cellular proliferation. So, in conclusion, literature data show that there is still currently limited evidence for adverse effects in workers exposed to any of the most used nanomaterials. The respiratory tract was investigated as the primary target organ for carbon, metal, or metal oxide-based nanomaterials. Persistent inflammatory and oxidative stress reactions may determine the biological alterations induced by nanomaterials, but in the future, longitudinal epidemiological studies are needed to define suitable dose-response relationship that can be useful to predict from the dose, from the exposure, the possible health effects, the health impact the nanomaterials will have on the health of exposed workers. Thank you for your attention.
Thank you, Dr. Velusca. Please, if anyone from the audience would like to make any question to Dr. Velusca, we invite you to do it, please. And if you prefer, you can also type your question on the chat, and then we can make the question at the end of the webinar too. Okay. Okay, now we have one question, Dr. Velusca. It comes from Dr. Renato Vargas from Peru. So let me check. What types of personnel protection equipment is used to prevent respiratory exposure?
Okay, thank you for the question. That is interesting and intriguing because generally, from an occupational point of view, an occupational medicine point of view, what we do to protect workers exposed to nanomaterials is general what we do for workers that are exposed to chemical risks. And so, in general, the protection are the same that we use for chemical risk and that we use for chemicals that are not present at the nanosized dimension. These are the approach that we have today, that we consider today. We don't have specific protection to specific focused on nanomaterial exposure, but we have to consider this exposure as a general chemical exposure, and so we have to protect against the chemical risk.
Okay, thank you, Dr. Veruska. Anybody else would like to make a question to Dr. Veruska? Oh, there's another question from Dr. Renato. Since nanomaterials are quite small, can they be catched by current filters?
It's very difficult to define to respond to these questions because literature data are so quite conflicting in these results. I'm not sure that that the protection can be enough. The protection that we currently have for workers and for general chemical risk could be enough for also for ultrafine size particles. But it's what we can do today.
Thank you, Dr. Veruska. I would like to make one more question. When we talk about monitoring the exposure, the risk exposure to the nanomaterials, which recommendations could you give us? I mean, technical aspects that we should keep in mind for our monitoring risk exposure to nanomaterials?
Okay, yes, thank you for the question. And I think that also the speakers that follow me maybe could respond also better because they'll focus their presentation on the exposure topic. But generally, there are some key issues to take into consideration in nanomaterial exposure evaluation. The first is that the dosimetric parameters that we generally use to assess the exposure to particulate matter cannot function so well for ultrafine size particulate matter. And so maybe the suggestion is to adopt a multi-phased approach to assess the exposure. So not only the exposure and to address the exposure as a mass, as we generally do for particulate matter, but also as a concentration number, for example, of particles or lung surface area. So there are different parameters that can be more representative of the effective dose the nanomaterials may have. And so they may be more representative of the possible they may be more representative of the possible relationship with the adverse effects. Concerning biological monitoring, some studies that also our group of research has done tried to identify in biological fluids, for example, the content of metal or metal oxide-based nanomaterials. So research is going on in trying to identify specific biomarkers of exposure. So the suggestion is to work on environmental monitoring together with biological monitoring and to try, according to the most advanced knowledge, to try to define standardized procedures to assess the exposure, because now we don't have enough information to define internationally standardized procedures both for the environmental and the biological monitoring. But I think that this will be the focus of the next presentations.
Thank you, Dr. Veruska. In order to conduct in the best way the discussion, and it's open for all the speakers, we're going to leave the time for the questions and answers to the end of after all the presentations. So thank you, Dr. Veruska, and I'm going to introduce to our next speaker. So now we have, it's my pleasure to introduce you to Dr. Enrico Bergamaschi, who is Professor of Occupational Health at the Faculty of Medicine, University of Torino. He's medical doctor and holds a PhD in occupational medicine and industrial hygiene. He's occupational physician since 1990. He's member of the EU Initiative Nanosafety Cluster and of the EU-USA Community of Research. The research activity carried out in the field of industrial and environmental toxicology has been aimed to identify biomarkers of exposure, internal dose of early effect on critical organs, central nervous system, kidney, lung, and others, following exposure to xenobiotics and at assessing their applicability to the study of populations of workers occupationally exposed to chemical agents and risk groups of general population. He has coordinated UNITO research unit, a multidisciplinary team consisting of occupational physicians, PhD students, biochemists, and technicians. His team was in charge of first carrying out a critical evaluation of current data on biological effects and existing biomarkers of nanomaterial exposure, and selecting a panel of already valid biomarkers of exposure and early effects. His team also set up tools and methods that they formally recorded in a harmonized protocol together with Unisante. They engage companies and coordinate the field studies in Italian factories to apply the research protocol, analyze the biological matrices for the quantification of biomarkers and field in the database. It was actually a collaborative effort as well as a hard exercise of Dr. Enrico and his team. So welcome, Dr. Enrico. It's a pleasure to have you with us during this webinar.
Thank you, Norville. Thank you, Cecilia, for this nice invitation. I hope to be complete what already Veruska told you. I try to share my screen. Speriamo di riuscirci. Okay, do you see my screen?
Yes.
Okay. There is okay. So thank you so much. As Veruska told you, epidemiological evidence regarding health effects in humans due to exposure to nanomaterials is currently limited. Epidemiologists, like occupational physicians, face scientific, methodological, political, and regulatory challenges in identify and enrolling sufficient participants in a cohort for the study. Exposure assessors need to find new methods, as conventional mass dose-based airborne concentration is insufficient for quantitative exposure assessment of nanoparticles. Even though 40 studies are still available, most of the epidemiological investigation of nanotechnology workers were cross-sectional. So the validity and reproducibility of biomarkers were not assessed due to generally small study samples used and methodological limitation of most available studies. These studies found limited evidence of adverse effect in workers exposed to the most commonly used engineered nanomaterial. Even so, some biological changes were suggestive for subtle and mild adverse impact, the primary targets being the respiratory and cardiovascular systems. Changes in biomarkers level compared with control were also observed. However, limited exposure data and a relatively short period since the first exposure may have influenced the prevalence of adverse effects found in epidemiological studies. To overcome the exploratory nature of these studies, we established an international cohort within the ULife NanoExplore project to carry out a multi-center prospective study and to address possible health effects from occupational exposure to nanomaterials. We, as you also remember, developed a harmonized protocol integrating quantification of airborne nanoparticles with biomarkers in exhaled breath condensate and urine to build a registry of workers to follow up studies. The study involved 3 projects partnered countries, Switzerland, Italy, and Spain. In each country, the participating companies were enrolled based on confirmed prior knowledge of their activities related to the handling of nanomaterials. A walkthrough visit was conducted for the 5 companies handling nanomaterials by the company environmental health and safety professional, together with occupational physician, with occupational hygienist also associated with the study. Workers identified as potentially exposed and non-exposed were invited to participate in the study, and workers who provided a written consent for participation were included in the cohort. Exposure assessment relied on a multi-parametric strategy. Airborne nanoparticles were measured over a work shift of 6-8 hours for 2 or 4 consecutive days, depending on the facility, using a direct reading optical particle counter like this mini, which measures the particle number concentration within a detection range of 501 million of particles per cubic centimeter, the particle size, and the lung deposited surface area, which is the probability, which corresponds to the probability of particle deposition in the tracheobronchial and alveolar regions of the lung, and is considered the most relevant exposure metrics with respect to nanoparticles toxicity. Here, I give you some examples of monitoring activity. I am very quick in this illustration because you can see better with the slide I left you. But this stress, they highlight the higher variability of exposure when we use real-time monitoring, for instance. This is a very, very common picture of exposure. We confirm the presence of the reported nano objects handled at each company by transmission electron microscopy and energy dispersive X-ray for composition analysis. But go to the epidemiological samples, the workers. We recruited 141 participants from 7 companies, 2 research facilities with confirmed absence of nanomaterial exposure, and 5 companies with confirmed nanomaterial activity. The health status and confounding variable were investigated by a proper questionnaire, a so-called epidemiological questionnaire. In this population, we assess a battery of biomarkers of exposure and their effect, reflecting specific mechanisms of action like Verushka remembered you before. The following table summarizes the mean value of biomarkers with their corresponding interquartile range. ABC biomarkers in exhaled breath condensate concentration were in general higher among exposed compared to controls, and in accordance with concentration reported in the literature. The same were in urine. But further analyses were carried out by assuming causal relation between nanomaterial exposure and an effect marker as depicted by directed acyclic graph. So not only an association, but a possible causation. Particle number concentration and lung deposited surface area were used as fixed effect independent variables and fitted for each biomarker in separate models. The following tables present the regression coefficient, that is the direction and strength of the relationship for particle number concentration and LDSA respectively. 8-isoprostane, a marker of oxidative stress in ABC, was strongly and positively associated with both metrics, but these associations lost their statistical significance after the adjustment for confounding variable. We observed consistent positive relationship between cytokines, interleukin-1, interleukin-1 beta, and TNF-alpha, with both metrics. This relationship remains statistically significant after adjustment for potential confounders. Urinary total antioxidant capacity, you see here, was negatively associated with both metrics and remains statistically significant with the same effect size after adjustment for potential confounders identified by DAG. We also conducted a stratified analysis to assess whether exposure to a particular type of nanoparticles would have an association with the different biomarkers. We created 5 binary variables for exposure, yes or no, black carbon, titanium dioxide, silicon oxide, carbon nanotubes, and calcium carbonate nanomaterials that were the more representative. The models were performed both with and without adjustment according to the confounding variable. Exposure to any of the nanomaterial types induces an increase in 8-isoprostane in ABC. Exposure to black carbon and carbon nanotubes, here you see, significantly increased KL6, a biomarkers of interstitial lung fibrosis. We observe an increase in KL6 in ABC of workers handling carbon nanotubes and also silicon oxide, both chemical known to induce lung fibrosis. But exposure to all the nanomaterials were associated with an increase in cytokines. This study offered new insight into the development of early biological response in workers after exposure to different types of nanomaterial, which is the true picture of real world. Taken together, the results suggested an activation of the innate immune response rather than an oxidative stress as the main effect of the mixture of nanomaterial investigated. The most notable findings were the significant increase in cytokines. Just another thing were investigated. For instance, we also investigated the relationship between the dose nanoparticle analysis, so the measurement of particle breath condensate, and we found a relationship, a sort of dose response relationship with the number of particles and the biomarkers of inflammation. When we talk about inflammation, we don't talk about acute inflammation. We talk about chronic inflammation. So these changes, these physiological or paraphysiological changes are quite stable over time. So they fix a chronic inflammation status. Since the number represent the main targets for exposure, we also assess the relationship between lung function parameters and nanomaterial exposure. In particular, we investigated the predicted worsening of lung function in 10-year exposure. Sorry. Just a few, just a minute. Our findings suggest that independently of lifelong tobacco smoking, ethnicity, age, sex, body mass index, and physical activity habits, 10 years cumulative exposure to nanomaterial is associated to worse FEV1, a FEV 25-65%, which might be consistent with the involvement of both large and small airway components and the early sign of airflow obstruction. Sorry, you heard me?
Yes, we can hear.
Okay, sorry. Because I have the screen blocked, they did not proceed. Anyway, just to conclude my talk, what is the meaning of this project? I told you only a part of the main finding of this project. Workers occupationally exposed to nanomaterial showed high levels of inflammatory biomarkers as compared to non-exposed workers. Inflammation seems a more sensitive endpoint as compared to oxidative stress, which is seen in vitro studies. We provided evidence of the relationship between increasing exposure to airborne nanomaterials and the burden of particles in the airway by nanoparticle tracking analysis, which also explain a measurable to mild decline in lung function in the high exposure subgroups. Many biological markers show a dose response trend, suggesting that a no effect threshold could be identified. Finally, although not nanospecific, such biomarkers also suggest early to probably reversible health effects, which deserve to be assessed on a larger cohort and in a long-term perspective. So thank you for your attention.
Thank you, Dr. Enrico, for such great presentation and for sharing your experience during all this project, leading this project. We will leave the time for questions and answers after the last presentation. So we hope you can still be with us for the discussion. And now I will introduce our last but not least important speaker, Dr. Ivo Clavicoli. Dr. Ivo, oh, sorry. Dr. Ivo is a full-time professor of occupational medicine. He holds a degree in medicine and surgery from the Università Cattolica del Sacro Cuore, sede di Roma. He holds a specialization on occupational medicine at the same university. He holds a PhD in occupational medicine and industrial hygiene at the Universidad de Milan. He is the author of over 400 scientific publications. He has an H index of 58 on Scopus and 66 on Google Scholar. He's a member of the editorial board of the following journals: Science of the Total Environment, Human and Experimental Toxicology, Journal of Occupational and Environmental Medicine, and Giornale Italiano di Medicina del Lavoro e Ergonomia. He was an associate editor of the international journal Dose Response and is currently an associate editor of the following journals: Toxicology and Industrial Health, Journal of Occupational Medicine and Toxicology, and La Medicina del Lavoro. Welcome, Dr. Ivo. It's a pleasure to have you with us during this webinar.
Okay. I share my just a moment. Sorry, but I have some problem with the if you, Norville, can help me.
Oh, please.
Because you have the presentation.
Yes, I can share your presentation.
Okay, thank you. Thank you. And sorry, but we have some problem with Apple.
No, never mind. I'm going to share your presentation.
Okay.
It's in PDF, but it works. So
okay.
Please let me know if it's working.
Sorry, this. Okay. Thank you so much, and sorry for this situation. Good morning, everybody. I would like to thank you, Norville, for the invitation, but also Professor Leso and Dr. Colautti for giving me the opportunity to provide my contribution in this webinar. And I will talk about the risk assessment and management for a responsible nanotechnology development. Please, the next slide. And as the next, please. Okay. As we have heard in the previous presentations, the knowledge concerning nanomaterial is still in a formative phase. And in this uncertain scenario, it is essential to establish robust and suitable strategy for the risk assessment of nanomaterial. And in this sense, the core step in such assessment include the hazard identification finalized to determine the specific physicochemical nanomaterial properties that may pose risk to human health. Hazard characterization, a step focusing on understanding the condition under which these xenobiotics may exert harmful effects, thus requiring the analysis of the dose-response relationship and the underlying mechanism of toxicity. The third, the exposure assessment that depends on the availability of validated analytical methods capable of detecting and quantifying nanomaterials in occupational and environments. And last, the risk characterization, the final step, integrating the finding from previous phases, able to provide a comprehensive evaluation of a potential risk. The next slide, please. However, despite such established framework, significant uncertainties remain across risk assessment components. In particular, hazard assessment is challenging by the lack of a comprehensive characterization of nanomaterials in terms of both intrinsic and extrinsically acquired characteristics that can influence their toxicological profile. Also, the molecular mechanisms underlying nanomaterial-induced adverse effects are still poorly understood, and the methodologies, including innovative techniques, as we have seen, the investigation of these mechanisms are not standardized. Concerning hazard characterization, existing toxicological data are often derived from studies from considerable methodological heterogeneity, frequently based on the in vitro and animal models that don't adequately represent the low-dose, long-term exposure scenario typical of workplace environments. This limits the extrapolation of experimental findings to the human exposure context. This limits this, also the experimental findings to human exposure context. Moreover, as regard the exposure evaluation, the environmental behavior of nanomaterial remains largely unknown. And no definitive strategy for the environmental and biological monitoring have been internationally standardized. Given these uncertainties, a precautionary risk management approach seems necessary, including proactive strategy to protect the health of workers potentially exposed to nanomaterials, even in the context of limited toxicological data and insufficient quantitative exposure estimates. Please, the next slide. To this aim, the control banding has emerged as a precautionary and pragmatic strategy for the qualitative and semi-quantitative assessment and management of risk associated with exposure to potentially hazardous substances. Several control-banding frameworks have been developed and implemented across various countries. Some examples include the control-banding nanotool in the USA, the Swiss precautionary matrix, the Stuff Manager Nano developed in the Netherlands, the ANSYS tool in France. And control banding is based on the widely accepted risk paradigm, where risk is defined as a function of the hazard severity and exposure probability. Both dimension, hazard, and exposure are characterized into different levels of bands. These bands are then combined, often using a matrix format, to generate a risk or control band, which informs the recommended level of intervention aligned with the principles of precautionary risk management. The next slide, please. From in this slide, we can see that generally addressing potentially harmful exposure in the workplace, a hierarchical approach to risk management is widely adopted. At the top of the hierarchy is the elimination of substitution of hazardous substances. In the context of a nanomaterial, is aligned with the concept of a prevention through design, or in Europe, the safe and the sustainable by design. The concept of prevention through design is typical of a US context, while safe and sustainable by design in the EU, which promote the development of nanomaterials that are safer and environmentally responsible from the outset. Next, engineering controls are implemented to minimize exposure. This may include process containment, work isolation, ventilation system, modification to production processes to reduce emission potential. In addition to these latter, it is possible to adopt administrative control that contribute to enhance the effectiveness of occupational health and safety program. This measure include organizational strategies such as job rotation to limit individual exposure duration, risk communication protocols, worker education and training on safe handling procedures, and also occupational health surveillance, including biological monitoring, but also epidemiological research. Finally, we have the last step, the risk management, that include the adoption of suitable personal protective equipment that are the last measure. The next slide, please. As a practical example of nanomaterial risk management, the NIOSH, the National Institute for Occupational Safety and Health in US, recommends
sorry, Doctor.
Establish. Yes.
Your microphone, but now it's working. There was a problem with your microphone, but now it's working. Sorry.
Okay, sorry. As a practical example of a nanomaterial risk management, the NIOSH, the National Institute for Occupational Safety and Health in the US, recommends that employers who manufacture, use, or handle silver nanomaterials or products containing them establish a comprehensive risk management program. And this program should be developed with the active worker participation. This is very important. And include the following key components. The first one relates on the systematic identification of workplace processes and job tasks where potential exposure to silver nanomaterials may occur. It is followed by the development of a clear criteria for the selection, installation, and evaluation of engineering controls to minimize exposure. The routine and the systematic assessment of worker exposure to silver nanomaterials, and the implementation of training programs for workers. And other key points include the establishment of procedures for selecting and using appropriate personal protective equipment, and the development of a formal program to ensure effective respiratory protection for workers. The creation of spill response plans and the routine cleaning procedures seems also important, together with the provision on and washing stations to reduce dermal and oral exposure risk, and the adoption of appropriate health surveillance plans. The next slide, please. Overall, the responsible development of nanotechnology, the topic of my presentation, is absolutely interplayed with the protection and promotion of the safety and health of engaged workers. To this aim, it is important to advance knowledge on emerging nanomaterials and their potential health risks, better characterize the hazards associated with engineering nanomaterials, to create accessible and evidence-based materials to inform workers, employers, health professionals, regulators, and also policymakers about nanomaterial hazard, risk, and also management strategy. To support epidemiological research focused on nanomaterial exposed population, and last, to assess and to encourage adherence to national, but also international risk management frameworks and best practices. The next slide, please. In this context, some key principles should guide the research on nanotechnology. Occupational activities involving nanomaterials must not compromise worker health. This is very important. The first point. The second, it is necessary to establish harmonized definition of engineering nanomaterials. There is a lot of confusions about this one. Ensure communication and documentation or conduct through hazard and risk assessment to guide exposure control measures, to develop mechanisms to monitor and detect early signs of adverse health effects among exposed workers, apply suitable occupational hygiene strategy to mitigate nanotechnology-related risk, to adopt precautionary measures to protect worker health, to standardize measurement techniques and control strategy across nanomaterial, to sustain the right of workers to be actively engaged in development and in the implementation of workplace risk management practices. Thank you for your attention.
Thank you, Dr. Ivo, for such a great presentation and for sharing the experience with us during this webinar. And thank you to the Scientific Committee of Nanomaterials and Workers' Health for your support during this event. And now, with the presentation of the four speakers, we would like to open the discussion and we would like to invite the attendees to make questions to all of our speakers.
I think that we can give the possibility to all people to write to our email to ask information also on studies. I think it's the same also for Veruscalis and for Enrico Bergamaschi, and we are open to question now. But I think if you have the need to have other information, I think that we can give you the support, because I think that there is the possibility of probably in your country or in your activity, occupational activity.
Thank you, Dr. Ivo. Yes, it will be very helpful for the attendees. I will give an email so they can send an email asking for complementary information. And maybe we can, if you agree, maybe we can restart the discussion in the last question that we made to Dr. Verusca about the technical aspects we can consider for the monitoring of risk exposure when we talk about nanomaterials. We got one question from one of our attendees. What industries in South America might have incorporated nanomaterials in their process and, by instance, have the health hazard in their workplaces?
Sorry, lost a little part of your questions. Maybe are directed to my presentation. Which type of nanomaterial has been most dangerous in research?
Oh, actually, that's the last question, but there's one before that. The first question was, what industries in South America might have incorporated nanomaterials in their process and, by instance, have the health hazard in their workplaces?
I think that maybe Cecilia can provide something data,
Yes.
more updated data for South America.
Yes, sorry, but I have a horrible flu. And
Never mind.
yes, in Latin America, maybe you have two things in agriculture. Yes, construction, and also we have a lot of process related to some kind of related to the new materials in energy, and also in particular here in Argentina, we have some research in lithium, and different process. You have to see the process, and you have to know the process and where is involved the nanomaterials in this process to keep the risk out. Yes, maybe you can, if you want to know something about some kind of industry in part, may I share with you the knowledge in Latin America, and maybe also about the researchers in Latin America.
Okay. Do you have any experience, doctor, about exposure in occupational, in health workers that works with nanomaterials or nanotechnology?
In Latin America?
Yeah.
You have some research in Argentina. We focuses areas with the first industry here is a particular company. Maybe in some countries know it like nanotech. Yes, they have paints, they have they have some kind of respirators, and they have also a particular product in agriculture. Yes, and they want to have a research in particular in occupational health and the risk.
Sorry, Cecilia. I think that the question was related also to healthcare. And about the healthcare, there are various areas in the prosthetic sector, for example, in orthopedics and dentistry, and also in the pharmaceutical sector, for example, in the production and the development of drug carriers that are that use different nanomaterials. I think that is very important to remember this one, because there is a great use of nanomaterials in the health sector, and so we can have some exposure also in this context. But also there are other sectors, for example, energy sector. There are use of nanomaterials, for example, for the treatment of the waters, for example. And there are great use of nanomaterials, for example, also in the textile, in the using of the clothing industries, or also in the energy sector, in the electronics. There are very application of nanomaterials. I have seen also a question in the chat of the Eduardo Aguirre. Sorry if my pronunciation is not correct, but about the precautionary principle. I think that the context, if we know that nanomaterial exist and they are used in this occupational setting, I think that we must apply the precautionary principle. Their mere presence is sufficient because we have a lot of difficulties, as we have seen in the different presentation about the exposure assessment concerning both environmental and biological monitoring. So we can not have other way to adopt, in any case, the precautionary principle. If you have heard my presentation, the first aim of our activity is to protect the health of workers, and for this aim, it is important to adopt in this phase, in this situation, to adopt the precautionary principle.
Thank you, Dr. Ivo. We have another question from the chat from Dr. Cesar de Pool. Which type of nanomaterial has been the most dangerous in research? Is it due to the shape or size or to the organ damage?
I think that I can spend a couple of words on this in this sense because I think that there is not a type of nanomaterial that is the most dangerous in research. I think that there are nanomaterials that have been most investigated. Nanotubes are extremely widespread employed in consumer products like sunscreens, for example, or consumer like other products for hygiene, or in electronic devices and something like this. So there are a lot of nanomaterials that have been strongly investigated. And sure, I agree with the question. So which is the parameter that is the most relevant? The shape, the size, the surface functionalization. We don't know exactly at the moment, currently, which is the most relevant parameter that is responsible for the dangerous, the hazardous profile of these nanomaterials. Certainly, for problems of time, I have not detailed this aspect, but there are two kinds of nanomaterials that have been recognized for their potential carcinogenic, for their carcinogenic potential, that are carbon nanotubes, multi-wall carbon nanotube 7, that were recognized by the IARC, International Agency for Research on Cancer, and titanium dioxide in its ultrafine dimension. The carbon nanotubes, in a certain way, recall us the case of asbestos. And so they received a lot of attention in the first period of their employment. But the research is not finished, and we have to study a lot to define the genotoxic profile, the mutagenic profile of these nanomaterials, and the genetic, lot of issues that need to be addressed before defining the dangerous and the hazardous profiles of different nanomaterials. And the question is even more difficult, further difficult to address because of the multitude of nanomaterials. And so in occupational toxicology, we said that a risk assessment, not one risk assessment fits all nanomaterials, but each type of nanomaterial should be addressed according to a specific approach, considering the physicochemical characterization that is absolutely important, also from an exposure assessment point of view.
Thank you, Dr. Peruska. So based on what you just talked about, In countries such as Peru and Latin America, we schedule or we organize the medical surveillance programs to conduct medical examinations at least one time per year in activities such as construction and agriculture companies. But considering the nanomaterial exposure in those sectors, in those two sectors, could we change the frequency of medical examinations and to make it more frequent, like twice per year? Or which recommendations could you give us? When we talk about exposure for nanomaterials in construction sector.
It is a very old problem because we are discussing about the best test, the best way to carry out health surveillance. But actually, till now, in my opinion, there is not a true answer, reliable answer to this question. I think that we should focus, however, on some target organs, and which is not only the respiratory system, but also the cardiovascular system in particular. And we also should, in my opinion, okay, we are talking about engineered nanomaterials, but nano-size materials are present in many dusts we are usually managing as occupational health professionals. So also in cement industry, in construction, as you also remember, and many other industry, there is a different proportion of ultrafine particles that are usually less relevant in terms of mass, but very important in terms of reactivity. So the surface reactivity is just one of the parameters that deserve to be investigated, but is not measurable easy or routinely, but is important. And so the question is what is the best protocol of health surveillance? I think that we should assess case by case, unfortunately, by now, and to investigate on the basis of the knowledge what are the main organs that can be involved. Actually, there is a systemic dissemination of ultrafine particles, like air pollution, and it is quite easy to identify one specific target. There are multiple targets, unfortunately. However, there are also some ways to protect workers, not only from the medical point of view. When you asked before about the respiratory protection, in some very dusty environment, the respirators is mandatory, but you can use routinely FFP2 mask, which is quite effective. In our study, in my experience, even though the workers' higher exposure, according to the measurement, external measurement, had less effect as workers thought less exposed because that didn't wear any personal protective equipment, also for respiratory. So many things can help.
Thank you, Dr. Enrico. have some comments in the chat. Well, this was excellent. Thank you from Dr. Cameron. Dr. Cesar just mentioned, I agree, even epidemiologically, if there is no protection, 100% of those workers exposed will enter to the incidence and prevalence. So we invite also to the attendees to make any other question. I would like to make one question for the first speakers. When we talk about designing a research project and based on your academic experience, research experience, when we start from zero in countries such as in Latin America.
Sorry, but we don't hear you.
Oh, sorry. Now you can hear me better? Sorry, you can hear me?
Yes.
Yes. I apologize. I would like to make a question. When we start from zero in research projects in focus on nanomaterial exposure, which recommendations you can give us when we focus on construction or agricultural companies and we want to make a research on this nanomaterial exposure in workers?
I think that you have to verify if there are nanomaterials. I think this is the first point to start your investigation, because I'm not sure that you have the possibility in this context to have the contact with the engineering nanomaterials. I think that, as Enrico anticipated in previous speech, there is the possibility to have exposure to incidental nanomaterials. But anyway, in this, I think that there are a long history and a long tradition of information about the possibility to have a good health surveillance for this type of workers. I think that is very important, for example, to have a medical examination every year. Can be very important with spirometry, and also to verify some biomarkers for a cardiological evaluation. I think this is the possibility that we have. For example, for engineering nanomaterials, about 10 years ago, ICOH proposed the medical examination with the engineering nanomaterial every 3 years. I think that choice is for the type of occupational setting that you ask is sufficient and health surveillance every year, and verifying the lung and also the global. I think that is good. Sorry, Norval, but I have to leave you now. And I don't know if the same for Enrico and Ferruccia, but in Italy it's too late now, and
Okay.
we have exceeded our allotted time. But anyway,
Anyway, it was a pleasure.
Thank you
Thank
so
you
much
very much for your support and for giving us this good opportunity to share our knowledge to your context, to the South America that is in our heart, as a lot of you know. I think it's Cecilia firstly, but also I've seen that there is also Carlos, and goodbye.
Thank you so much to the four of you, and we hope you can join us in future activities. And thank you to all the attendees too. See you. We will share the recording to the emails that we just get from the participants. And well, thank you all.
Goodbye.
Goodbye.
Thank you.
Bye.
Goodbye.
Thank
you.
For the
Goodbye.
Bye
speaker.
from Italy.
Thank you.
Thank you so much.
Thank you.
Thank you. Thank you.
Thank you.
Thank you.